Okay, so let's do the problem 3 together. We want to check if the AD is a key of the relation or not. We check this by checking two things, right? If you still remember, it's very similar to problem 2. Is it equivalent? In other words, you check. The first thing we need to check is AD a super key, right? Or the closure of AD covers all the attributes, right? Right. These two are equivalent. Is AD a super key, or the closure of AD covers all the attributes of the relation R or not? So they are equivalent, so we can remove the first one. We just focus on the closure of attributes here. And we need to check this one. Besides this, we also need to check another thing. What else do we need to check? We also need to check none of its subsets can be the super key. And what are the subset of AD, right? What are the subset of AD? It can be either A or D, right? None of A or D can be the key, right? Can be super key. Or none of A closure or D closure can cover all the attributes, right? Can all cover all the attributes of relational. We need to check two things, right? The first part is to check the closure of AD to see if it can cover all the attributes or not. And we also need to check the closures of its subset. We need to make sure none of its subset can cover all the attributes. We have computed this D closure already, right, in the problem 2. And then let's do this problem together. Let's calculate the AD closure first. AD closure equals to what? You should be able to provide me with your answer, right? You can do this problem iteratively by following this algorithm we showed before. Right? I don't want to write down the process again, and we do this in a very fast way. I hope you can follow me. And so we start the closure of AD, right? We check this FDs. We check both left-hand side and right-hand side with AD, right? And so right now we have AD in the closure set. Then we can check the left-hand side. B, no, right? We don't have B here. We ignore this one. D implies E. We have D here. We don't have E. Therefore, we have to add the E into the closure set, right? We have B implies A. We don't have B. We ignore this one. E implies C. We have E here. We have to add a C here, right? We have AD implies B. We have A. We have D. We don't have B, right? Then we have to add a B into the closure set. And we start the process again. B implies CD, right? We have B. We have CD as well. We ignore this one. D implies E. We have E already. B implies A. We have B already. We have E implies C. We have C already. AD implies B. We have B already, right? In other words, in the second loop, we do nothing, and we will stop and return. The closure of the AD equals to what? Equals to A, D, E, C, B, right? If we reorder the attributes, we can get the closure of AD equals to what? It equals to A, B, C, D, E, right? So it covers all the attributes. So AD is a super key or relation R. Besides this, we also need to check what? We also need to check none of its subset can cover all the attributes. In the problem 2, we have calculated D closure already, right? It equals to what? It equals to C, D, E, right? It is not a super key, right? Since D closure cannot cover all the attributes. And we also need to calculate what? We also need to calculate A closure, right? A closure equals to what? We check the left-hand side. In the very beginning, we have A closure equals to A, right? And then we can check all the FDs. B, no. D, no. B implies A, no, right? E implies C, no. AD implies D, no, right? Therefore, we have the A closure equals to what? Equals to A, right? So it's not a super key neither, and it cannot cover all the attributes, I mean its closure. So based on what we have AD is a super key, and now its subset can be a super key. Therefore, we can conclude AD is a key, right? Overall. I hope you can follow me, right? The process is very similar. We calculate the AD closure first to see if AD closure can cover all the attributes or not. If so, then we can say the AD can implies all the attributes in the relation. So AD is a super key, right? We will check its subset. Its subset covers both A and D, right? We have the D closure covers C, D, E. It's not a super key, right? Because its closure cannot cover all the attributes. We have the A closure equals to A. It's not a super key neither, right? Because the A closure cannot cover all the attributes. According to the definition of key, AD is a super key, and now its subset can be a key. Therefore, we can conclude AD is a key for the relation, right? So this is the answer to problem 3. I hope you can follow me. And let's do the last problem together. Is ADE a candidate key of the relation or not? This one should be very easy to answer. So first of all, I need to clarify what is a candidate key, right? Candidate key is just equals to key candidates. It is a key, right? It is a potential option to serve as a key. Because given a relation, we can find multiple keys, right? We showed before. We can have different options to use. We can have different choices of the keys for the relation. We can have different choices of the keys for the relation. Each key will be a key candidate, right? And the question we're asking here is, ADE is a key candidate or not? You should have the answer in your mind already, right? So to answer this question, we need to follow the definition, right? So we need to check first to ADE is a candidate key or not. We need to check if the first thing is the closure of ADE cover all the attributes, or and now its subset their closure can cover all the attributes. Right. Probably we don't need to do the first one because we can already find out one of the subset can serve as a key, right? According to the problem 3, we know AD closure equals to what? Equals to A, B, C, D, E, right? It is a key, right? So therefore, we find one subset of ADE, and which is AD, right? It can serve as a key already. Therefore, we can conclude ADE is not a candidate key because one of its subset is a key already, right? So therefore, it's not a candidate key for the relation, right? So I mean, if you follow the process, you can derive the ADE closure first. I'm sure we can get ADE closure equals to A, B, C, D, E, right? Covers all the attributes. because AD covers AD, right? AD can already imply all attributes, not to mention ADE. And then the second condition, we will check none of its subset their closure can cover all the attributes. However, we can find one counterexample, AD, right? Its closure can cover all the attributes and it's the key according to problem 3. Therefore, we can conclude ADE is not a candidate key for the relation in the problem 4. So this is the answer we can provide for the problem 4. I hope you get the right answer as well. Okay, so this is the example. We also have the example in the slides, and you can check your answer in the slides as well. And generally, it covers the same information. Okay, so that's it for the example. Let's move to the next page.